Right, so that's the, call it pictorial view. What we normally do in statistics is we use what we call averages. And there are various forms of averages, and I don't want to spend too much time on that. I've got to keep an eye on Mike because I tend to get excited about this and get carried away. Okay, so what we then want to do is we want to start expressing that graph in some kind of numerical way. So we want the sample of observations to include an aspect of central tendency, as we like to call it, and it becomes a single number that relates to the center of the distribution. And we call that an average, and the one that we generally use in statistics is the mean. And what I'll do is I'll take all the lengths of the people in this room, add them together, divided by the number of people, and I will have a mean. Okay, so there, population mean is the sum of all divided by n. Okay, and that gives me a figure. And I can say that the mean height of people in this room is 6 foot 1 inch and, well, 1.5 inch, whatever the case may be. And immediately, if I say to you that the average height of people in this room is 6 foot, you can get a picture of what's going on in that population. Okay, so it becomes a valuable numerical tool. More often than not, we can't measure the whole population, so we take a sample out of the population. We work out the mean in exactly the same way, we just use slightly different nomenclature to sort of distinguish between population mean and sample mean, but the same thing. We can also calculate the mean of the frequency distribution based on the frequency in each class and so forth. I'm going to put that in the notes, I won't spend too much time on it. There are also some other values of average, or other means of defining the average. We use a thing called the median. The median is actually the middle observation of a set of variables. That's very useful when we have extremes, like you've got these numbers and suddenly you have this extreme. So the median is then, because that extreme can then bias your mean, so we use the median. And the other one advantage of this is that very often if you've got missing plots, you can then take the middle value and get an idea of what's going on in the population. And then the other thing we often use is what we call the mode, and that's basically the class frequency that has the most observations. Those have their value, but generally we're interested in the mean. Okay. The other thing that you will notice about a population is the variation that occurs. So if I say the population or the height of people in this population, which is this room here, is 6 foot. You've got one picture, but you don't know if there were short people, tall people, and how many on either side. Were we all 6 foot? Was the average 6 foot because there was one person who was 10 foot and there was another one who was 3 foot? Okay. And the idea is that when we look at a population, we need some measure of variability. There are two populations. They have the same mean value, or the same sort of form. The one is just low variability, the one is high variability. And we need some kind of way of expressing that. Now, one of the things we use is a thing called the range, and we have numbers that vary from 3 to 26, and I'll say the range is 23 units. Sometimes useful, so I can say the shortest person here was 3 foot and the tallest person was 10 foot, but it doesn't tell me much about in between, okay? So it only takes into account the highest and lowest and doesn't provide an indication of how that data is distributed. And that is important as well. And the unit we use there is the standard deviation. there's the formula for the standard deviation for a population. And essentially, what we do is we look at each individual, how it deviates from the mean, right? We divide it by the number of individuals, and we also take the square root. Now, why we square that is, let's say I've measured 3 people. The average height is 6 foot. Okay, he is 5 foot, he is 7 foot, and the average is 6 foot. If I take the deviations and add them together, I'll get to 0. Because he is minus 1 foot, he is plus 1 foot, and you get to 0. So essentially we square it to get rid of the negative effect. Okay, because any square is positive. Okay, when we do it in a sample, it's exactly the same, only different. And I'll get to why we don't use n there, but we use n minus 1 in a minute. But basically, it comes down to the same thing. How much time was? I need to. Okay. Okay. If I've got time, then I'm going to go to this example down here, just to show you what I'm talking about. Let me just find it. Now you can do that very simply on a spreadsheet. What I have here is I've got 10 samples of height. The mean of those 10 heights is 86.3. I then look at the difference between the mean and the actual observation, and I square it, add them all together. Okay, I like using my hand. Okay, right. I can then take that value, okay, divided by n minus 1, the number of samples, minus 1, and I'll get to that in a sec. We call that degrees of freedom. Square root it, and basically I get a figure that, in crude terms, mathematicians will probably argue with me, is sort of the average deviation on either side of the mean of that population. Now I'm going to leave this like this, and I'm going to give you the spreadsheet, and you can go and do it yourself. Okay, and it essentially is explained there, and you can work out the mean. This we call the variance. Before it's square rooted, the standard deviation is the square root of that, and I'll get to another value just now that we call the coefficient of variation. But essentially what you're getting at is that the standard deviation then provides you with a figure of the distribution around the mean. And the larger the standard deviation, obviously there's more variation, and the smaller the standard deviation, the less the variation. Right, you'll see in the calculation of the standard deviation of a sample, or you'll see I use the value n minus 1 and not n. Degrees of freedom is a concept that is used in many statistical analyses. Suppose we're told we have 5 observations and the mean is 50. Okay. We are asked to invent values of the observations. So in other words, I need to get to 50. We know that if I add or multiply 50 times 5, the total of those observations was 250. I can now choose any number of numbers, or I can choose 4 numbers. The 5th number is defined by the total. In other words, if I take numbers 100, 75, 24, 31, add them all together, I'll get to 230. The last number has to be 20. Okay. So when we're looking at samples of a population, okay, there's a difference between the true population mean and the sample mean. And that we have to take into account when we're looking at standard deviations and looking at various other things as we go along. Okay, because we are stuck with that last number. Okay, it's defined by the true population mean. And therefore, we always do our calculations based on degrees of freedom, and we leave room for that extra bit, or call it error, that we didn't measure. Okay, so that's basically why we use